Okay, so this is where we left off last time where we talked about vapor pressure and boiling. And I want to kind of start back at this curve that we've already covered before. And I just want to point out that we could plot vapor pressure versus temperature. And this is temperature in Celsius anyway. But there's a relationship, and it's kind of this curvy kind of relationship. If I plotted this in Kelvin, it would be the same kind of curvy relationship. And so we can see in general, as you increase temperature, you see an increase in vapor pressure. That makes sense. The kinetic energy of the system is increasing as you increase temperature, and they're getting more energy. The molecules are getting more energy to break free of the things that are holding them in place. So I want to look at a way that we can do some math and do some calculations dealing with this relationship. And in order to do that, we're going to try to linearize this relationship so that instead of having a curvy line, we can have a straight line. And whenever you have a straight line, then you can do things like calculate the slope, and from the slope you can get information. And what we're going to show you is, in this case, is from the slope of what I'm about to show you, we can get actually, this is how you can calculate the enthalpy of vaporization. And that relationship is called the Clausius-Clapeyron equation. Okay? And so essentially, as you plot the natural log of pressure against 1 over the absolute temperature, you get a straight line dependency. And that's what this is showing here. So natural log of pressure, I'll make this bigger so you can kind of see that. So you're going to plot the natural log of the pressure against the 1 over the absolute temperature. And when I say absolute temperature, I just want to remind you, I'm talking about temperature that's measured in Kelvin. If you do this in Celsius, it won't work, what I'm about to show you. So here is the equation that we use. It's called the Clausius-Clapeyron equation. And it is the equation that actually shows us this relationship, this straight line relationship. So we're plotting the natural log of P, so of course we'll want that there. So the natural log of P vaporization, and that's equal to, then it turns out, the minus delta H of vaporization, change in enthalpy of vaporization, divided by the universal gas constant, and that's 8.314 joules per mole Kelvin. So that's the form of the universal gas constant. We want the one that gives us energy, because we're dealing with energy when we have delta H vap. And that's times 1 over the temperature, and this is plus the natural log of a constant called beta. And beta is a constant that you can look up specific to a given, it's specific to a given liquid. So when you put all this together, this gives a straight line dependency. So when you plot natural log of the vapor pressure versus 1 over T, you get a straight line dependency. And look, y equals, here's your slope, which is, that's your slope, m, here's x, because that's what you're plotting against, mx plus b, your y-intercept. So the y-intercept here, that where you hit the y-intercept where x is 0, so the y-intercept for this is going to be the natural, it's going to be the natural log of beta, and then the slope is right here. It's going to be minus delta H of vaporization divided by R. And if you know the slope, we already know what R is, because that's the universal gas constant, is 8.314 over here. We can rearrange this and we can solve for the delta H of vaporization. So in this case, the slope is minus 3478, and we can simply just go in and multiply by R, multiply the slope by R, and boom, we got this 28.92 times 10 to the minus third joules per mole. Now, in order to get this information, we would need to plot several points. We'd have to take a long experiment where we measure the vapor pressure at a bunch of different temperatures, and then we can do this. It is possible to do this with just two temperatures and two vapor pressures, and that's something that can be derived. It's an expression. It's the two-point. It's known as the two-point form of the Clausius-Clapeyron equation. So let me show you the two-point form of the. Here is the two-point form of the Clausius-Clapeyron equation. And so the general idea here is you can actually do the analysis and actually come up with things like the change of the delta H vap by just measuring a temperature and a corresponding vapor pressure and another temperature and a different corresponding vapor pressure, and you can set up this relationship, and through this you can do all kinds of things. And so the vapor pressure of a normal boiling point is 760 torr, or 1 atmosphere. And so what we're going to do is we're going to do a little practice problem here and see how you do. Okay, so I'm going to move this up, and I'll leave this right here. So here's our practice problem. We're going to use methyl alcohol, methanol it's called, CH3OH. This has a normal boiling point, so that's the boiling point at 760 torr. That's going to be, excuse me, 64.6 degrees Celsius. So that's the normal boiling point. So normal, I meant to put BP. And then at in the delta H of vaporization for the methanol is 35.2, and that's kilojoules per mole. Oops, I put this in the wrong position. Let me try that again. That's kilojoules per mole. All right, and so the question is, what is the vapor pressure of this methanol at 12.0 degrees C, given this information? So you're going to use the two-point equation for the Clausius-Clapeyron, and you're going to plug in these values, and remember, so we can say, all right, if this is T1, the boiling point, then P1, because it's the normal boiling point, is 760 torr. And then the rest we can get there. So what we have to do first is, well, don't forget temperature here is in absolute temperature. So go ahead and turn off this video now and see if you can solve this problem on your own. I think that would be a useful thing for you to be able to do. To solve for what we're looking for is T2. We're given T1. We're given, sorry, you're not solving for T2. I said that wrong. You're solving for P2. We're given pressure 1 and temperature 1. We're given temperature 2, and we're given this. So all that's left over is P2. And we want to know, what is the vapor pressure at 12 degrees C? So go ahead and plug in these things and see if you can do the algebra and come up with an answer, and then I'll go through it with you. So go ahead, turn off the video, give it a shot. Either you didn't turn off the video, or you did. I don't know. But let's see how to solve this problem. So the first thing we got to remember, temperatures have to be in Kelvin. So we got to take 64.6 and add it to that value. That's the conversion factor, and we come up with 337.8 Kelvin. And T2, do the same thing. 12.0 plus 273.15, and that's going to give us 285. Okay, 0.2 Kelvin. So now that we got all these things, plug it in to the 2-point equation. So I'm going to do that. So I'm going to say, okay, we got natural log, excuse me, of P2 over 760 torr is equal to, and here's where we got to kind of be careful. If we look here, delta H vap is given, if you look, in kilojoules per mole, and R is in joules per mole Kelvin. So we got to make sure that these have the same units for joules. So it's probably easier to just take this value and convert it to joules. So then joules will cancel out as you have one above the other. So we'll say 35.2 times 10 to the third joules. That's how I do my conversions. I'll just take the kilojoules and say times 10 to the third joules, and we'll take that divided by 0.314, and that would be joules per mole Kelvin. So that takes care of that part. And now we plug in our values for temperature. So we got 1 over 337.8 minus 1 over 285.2. And what we get when we plug all that in, hopefully you'll get this relationship. You get the you get the natural log of P2 again over 760 torr, and this all comes out to minus 2.31. So now the challenge here is we got to get rid of this log sign. So to do that, all we do is take e to both sides. So take e to this value, e to that value, and e to that value. That will get rid of the log, and that will give us a number here. So after doing that, we'll get P over 760 torr is equal to 0.0993. Okay, multiply both sides by 760. That's P2, by the way, and we'll get that P2 is equal to 75.4 torr. So hopefully you got an answer like that, and you can see where this comes from. Now I want to talk about heating curves. A heating curve is when we start off with a substance at a certain temperature, and then we either remove heat or add heat. And then we calculate what happens in terms of the amount of heat either given off or released as it has absorbed more and more heat. And so if we're going to use, let's do the following example. Let's look at 1 mole, 1.00, we'll say moles of ice at minus 25 degrees C. All right? And we're going to heat up that ice all the way until it reaches 125 degrees C. So to go from minus 25 degrees C all the way up to 125 degrees C, we're going from ice to liquid to steam because we're going through 2 phase changes. Okay? So when we head in this direction, we're talking about a heating curve where we're actually adding heat. If we go in this direction, heat is being lost. And we can go either way. Just depends on what temperatures you're using and all that. So we can kind of think about the process then in phases. I keep saying phases, I mean segments, different segments. And to go from minus 25 degrees Celsius to 125 degrees Celsius is actually going to take 1, 2, 3, 4, 5 different segments. And in each of those segments, something different is happening, and that's what we have to pay attention to. So to begin with, we just begin the process by adding heat to minus 25 degree ice, and that heat is going to be absorbed by the ice molecules and turned into kinetic energy. So it's going to start wiggling and wiggling and vibrating more and more until finally it's warmed up to the point where melting can occur at 0 degrees Celsius. That's the temperature where the first phase change happens. So this is a phase change then that's happening. So we got melting. And all of the energy, instead of changing temperature, goes into the phase change. So we don't see a change in temperature because all the energy goes into releasing the solids into the liquids, into the liquid form. Once all of the solid is melted and all that's left is liquid, then the heat again is absorbed. It gets turned into kinetic energy, which changes the temperature again. So now we go from 0 degrees all the way up to 100 degrees C. That's the next point where the new phase, where the new segment happens. And in this segment is boiling. And boiling is getting liquid turned into gas. And so all of this heat that gets absorbed it doesn't change the kinetic energy of the system. It just goes into the phase change. Then what happens is once all of the liquid's turned into a gas, then the steam that results is heated. And the heated steam increases its kinetic energy and it changes temperature again. So we kind of have two sort of scenarios. We have a scenario where the heat is absorbed and goes into the kinetic energy of the system and elevates the temperature in the direction we're going because we're absorbing heat. And then as the other situation is where the heat is being absorbed and going into a phase change. So the phase is actually changing. You're going from solid to liquid, liquid to gas. So in this case, we have 5 segments. We have the first temperature change of the ice. Segment 2 is a phase change. Then we have another temperature change, and that's segment 3. Segment 4 is a phase change, and segment 5 is a temperature change. And so if you look up here, what we can see is that for the first phase, the energy that was absorbed to change the temperature was 0.941 kilojoules per mole. And then for this, all the energy that was absorbed to cause 1 mole of ice to melt is 6.02 kilojoules per mole. And then phase 3 is, segment 3 I should say, is a temperature change segment again, and this is the liquid now gaining in kinetic energy. And if you do that, you calculate the energy absorbed in that phase to cause the temperature to increase. It's 7.52 kilojoules per mole. And then as we go this direction and we start getting boiling, then the vaporization part, the steam formation, generates 40.7 kilojoules per mole. And then to get the temperature from 100, the steam from 100 degrees C to 125 degrees C is 0.904 kilojoules per mole. Now, in order to get the total amount of heat absorbed then by this ice to make this transition, you have to add each of these together, and you got to make sure when you do your calculations they all have the same unit. So usually we just make them all in kilojoules. It seems to be the easiest way to go. So we make them all in kilojoules, and so you'll sum all 5 segments together, and then you can get the total amount of heat that's absorbed as you go from 25 degrees C to 125 degrees C. Now, what I neglected to tell you is, yes, I transitioned from the Clausius-Clapeyron equation right to here, and this isn't really about the Clausius-Clapeyron equation. I just wanted to make that point. This is something called a heating curve, and it's kind of a different topic now. And I forgot to mention that when I did the transition. So let's look at how you can calculate the heat absorbed at each of these segments. So if we look at segment 1, we got ice, and ice is being warmed from minus 25 degrees to 0 degrees Celsius. So let's look at this. So segment 1, we have 1 mole of ice at minus 25 degrees C, and we use the expression that we learned in Chem 112, where we learned that heat is equal to the mass times the specific heat capacity times the change in temperature. And the change in temperature is given by T final minus T initial. Sometimes you'll see T2 minus T1. Okay? So then, as we do this calculation, we can get delta T from there. You look up that value for the given whatever phase you're in. In our case, we're looking up ice. And so we need to know the specific heat capacity for ice, and that's actually right here. And that's 2.09 joule per mole per degree Celsius. And then the mass. Well, we know we have 1 mole of ice, so that means we know the molar mass of ice, and that has 18 grams. So it's 18 grams per mole. So you just put in the values here, in here, and you get 941 joules. And what we tend to do is, like I say, we want it all in the same unit, so just put it all in kilojoules. Next is segment 2, and segment 2 is a phase change segment. Temperature isn't changed, so rather than figure out the heat associated with the temperature change, that's where we need the heat capacity. In this case, we need to think about what are we doing? Well, we're melting, and so we're going to use the heat of fusion, the enthalpy of fusion, that's melting. And if we're melting, this will be a positive value. If it's freezing, it'll be a negative value because heat is given off in order to freeze. So what we need to know is the number of moles. In our case, we had 1 mole of ice, times the heat of fusion, 6.02 times, kilojoules per mole. So we can calculate that, and we get 6.02 times kilojoules per mole. So now we've calculated the heat absorbed by both segments, and now segment 3 is heating the water and causing the liquid water to have a temperature change. So again, here's our T final, here's our T initial. We went from 0 to 100, that's initial. We went from 0 to 100 degrees. We can look up, sorry, I just realized something. This is incorrect. That was the value for ice. We need the heat capacity for water, for liquid, and it's 4.18 joule per gram per Celsius, which is correct down here. It just wasn't up here for some reason. Little typo, little mistakes get made. And then so we multiply that, because even we started off with 18 grams of water, well, we still 18 grams of ice, we still have 18 grams of liquid. That doesn't change. The geometry and density and all that changes, but the total mass doesn't. So we still have the same amount of water, whether it's ice, steam, or liquid. And so we multiply out this, and what we get is 7.52 kilojoules. So now we've calculated the kilojoules for each of the segments 1 through 3. Then we have segment 4. In segment 4, we know that we need, this is HVAP, not H of fusion. H of fusion was melting. This is delta H of evaporation. That's 40.7 kilojoules per mole. And we have 1 mole, so the math is easy. So now we have the heat absorbed to cause 1 mole of liquid water to evaporate into steam, to boil into steam, to do the phase change. So all of this is that segment 4. Then, just like we've done before, here, this is correct here. Just like we've done before, we take the final temperature, the initial temperature of that segment. We take, here's the specific heat capacity and 18 grams of steam, and we got 0.904. Now we add them all together. So we add all the segments together in order to get the total amount of energy that was stored that was not stored but absorbed. And so what do we got? We got, so we had segment 1, so Q total is segment 1 plus segment 2 plus segment 3 plus segment 4 plus segment 5. And when you add all those, not sequence, segment, dummy. When you add all those together, then just to remind you what we got for the values for each, segment 1 was 0.941 kilojoules. They're all in kilojoules. Segment 2 was 6.02. Oops, 6.0. Right, what you're talking. Okay, 6.02 kilojoules per mole. Segment 3, from what we did, was 7.52 kilojoules per mole. Segment 4 was 40.7 kilojoules. They're not kilojoules per mole. I keep saying that, but it's, let me say this, it's just kilojoules. And then this one was 0.904 kilojoules. Now, when you add them all together, what do you get? We get 56, whoops, 0.085 kilojoules. And then when we think about what's our significant digits, well, we only know it best out to this digit right here. Actually, no, we don't. We know it only to the 10th place because of this one right there. So we can say 56.1 kilojoules. So that's how you would figure out that's a lot of kilojoules that got absorbed by 1 mole of ice going from minus 25 degrees Celsius all the way to 125 degrees Celsius. So the next area we're going to get into are things called phase diagrams. And before I do that, though, I'm kind of going to just kind of end this segment so that I can put this up on YouTube, a small little segment, and then we'll get into phase diagrams. That'll be the next part that I'll have.